This is lecture 1 for Math 348, Mathematical Methods for Management. And what we're going to be studying for a large part of the semester is linear programming. So the textbook is by Hillier and Lieberman. It's a classic book. Like most textbooks, it costs too much money. But even though the current edition is the 11th edition, the core parts that we're going to cover are more or less unchanged in every edition. So if you can buy a used copy or an older edition of the book, that should be okay for practically everything that we do. I've also uploaded, I think from the 10th edition, chapter 3 onto Blackboard. So you should have immediately the text available for what we're going to be studying. This is an asynchronous course. This means that there are no lecture times online on Zoom. The lectures are recorded and posted to the YouTube channel and playlist for this course. So this lecture will be uploaded within the hour. So we're beginning to talk about chapter 3. Chapters 1 and 2 are background, and you should read them to get some understanding of what the subject of linear programming and its applications are about. But we're going to start right in with a basic prototypical linear programming problem. It's extremely important that you understand everything that's going on. And that includes the vocabulary that's used in the subject of linear programming. So in linear programming, the idea is that this is a practical subject. You have some resources that you can use in different ways, and the goal is to optimize the use of the resources. What does optimization mean? Well, it depends what it is you're trying to do. So for example, if you're running a business, it might be associated with the different ways you can use your limited resources. Your profit will change. And your goal might be to maximize your profit. So there is what is called the objective function, profit. And you want to allocate your limited resources in the best possible way to maximize the profit. Alternatively, for each of your limited resources, there might be a cost. And in this case, your objective function might be the cost of the various ways of allocating your limited resources. And what you want to do is to minimize the cost. So if the objective function is cost, a natural objective is to minimize it. That's sort of the general picture. And we're going to look at a model example of a company which is called the Windoor Glass Company. The glass company produces windows and glass doors. It has 3 plants, 3 manufacturing facilities. Plant 1 makes aluminum frames and hardware. Plant 2 makes wood frames. And plant 3 produces glass and assembles the products. So your resources are the plants, which have different capabilities, and also how much time each plant can devote to the project. So our company, the Windoor Glass Company, is introducing 2 new products. So the first product, product 1, is an 8-foot glass door with an aluminum frame. Product 2 is a 4 by 6 feet double hung wood framed window. And the question will be, what mix of products, given whatever constraints we have, which are the times available for producing the product in the 3 different factories, how do you allocate the time in those factories? That's your resource. To produce a mix of products that generates the biggest profit. And we assume there are always assumptions in these models. First assumption is that the data that's given to you is correct. If you're an operations research person who's been hired to try to help a company out with a certain problem, you depend on the data that they give you. So there's always a question about the reliability or the accuracy of the data. Not necessarily that they're trying to give you the wrong data, but they simply might have the wrong data or might not know exactly what the right data is or how to figure it out. And we're making an assumption here that no matter how many glass doors are produced or how many windows are produced, the company can sell them all. So producing the product means an immediate sale and immediate income. So what are the units that are being used? So the products are produced in batches of 20. So you can't say we're going to produce 13 aluminum doors. You can say 20, 40, or 60, or 1, 2, or 3 batches. So the products are produced in batches of 20. And what data do we need in order to understand, to try to figure out the best use of the resources available? So the first is the number of hours of production time available each week in each plant for these new products. So you have 3 plants, and a plant can run 30 hours a day, for example. There's only 24 hours in a day. And maybe there are other products that are being produced. So there's a certain number of hours where each plant can be used for one or the other of these 2 new products. So how much time is available in the plant? The second piece of data you need is for each batch of this new product, how much time does it take? Suppose you have 4 hours available in plant 1, and to make 1 batch of the product takes 2 hours. So then the most you can make is 2 batches, right? So this is the production time used in each plant for each batch of the new product. And then you have to know how much money you make. For each batch of each new product, what is the profit? So you need the number of hours of production time available per week in each plant, the production time used in each plant for each batch of each new product, and the profit per batch of each new product. So let's say here in this prototype example is the data. So this is the data for Winder Glass Company. 3 plants, 1, 2, and 3. In plant 1, 4 hours of work time are available. In plant 2, 12 hours are available. And in plant 3, 18 hours each week are available. And how much time does it require to produce 1 batch of the product? Well, for product 1, to produce 1 batch takes an hour from plant 1. Plant 2 is not used at all, and it takes 3 hours from plant 3. So the production time per batch in hours for product 1 for plants 1, 2, and 3 is 1, 0, and 3 respectively. Product 2 is completely different. To produce a batch of product 2, you don't use plant 1 at all. It takes 0 time. But in each of plants 2 and 3, it takes 2 hours of time to produce 1 batch. And what is the profit? Well, for every batch of product 1, you make $3,000. And every batch of product 2, you make $5,000. And because we don't need to have all these zeros, we can say that we're counting profit in thousands of dollars. So the profit per batch for product 1 is 3. That means $3,000. The product per batch for product 2 is 5. That means $5,000. So then you have to make a mathematical model that covers, includes, presents all of this information. So let's say X1 will be the number of batches of product 1 produced per week. And X2 is the number of batches of product 2 produced per week. And Z is the total profit per week in thousands of dollars from producing these two products. And the question is, how do we choose X1 and X2 subject to the various constraints we have on the problem that maximizes this number, which is traditionally called Z, which is the total profit. And for any given value of X1 and X2, you make $3,000 for each batch of batch of product 1. So 3X1 is how much money you make, the profit from X1 batches of product 1. 5X2, this is the number of thousands of dollars that you make for each batch of product 2. So if you make X1 batches of product 1 and X2 batches of product 2, your total profit Z is 3X1 plus 5X2. This is what is called the objective function. And what were the constraints? Well, X1 less than or equal to 4. How did we get that? Let me go back and look. For plant 1, you have at most 4 hours of time available. It takes 1 hour for each batch of product 1. So X1 batches will take X1 hours, and you have at most 4 hours. So X1 is at most 4. That's where this first inequality comes from. In general, the constraints will be inequalities. So X1 is greater than or equal, is less than or equal to 4. Because there's one other constraint that always applies, almost always applies. It's a so-called non-negativity constraint. You can't make a negative number of batches. So X1 is greater than or equal to 0. X1 can't be negative. There's this non-negativity condition. Where does the second inequality come from? The second constraint. Let's go back to the table again. In plan 2, you have 12 hours of time available. For each batch you want to make of product 2, it takes 2 hours of time in plan 2. So X2 batches will take 2 times X2 hours, and they're at most 12 hours. So 2X2 is at most 12, or you can write that X2 is at most 6, just divide by 2. But that's the second inequality. What about this third inequality, which looks a little bit more complicated? Let's go back to the data. Let's look at plan 3. At most 18 hours of time are available in plan 3 for producing product 1 and product 2. One batch of product 1 takes 3 hours of plan 3's time. One batch of product 2 takes 2 hours of plan 3's time. X1 batches of product 1 will take 3X1 hours of time in the plant. X2 batches of product 2 will take 2X2 hours in the plant. So 3X1 plus 2X2, that's how much time it will take to produce X1 batches of product 1 and X2 batches of product 2. And that's at most 18. It's only 18 hours of time are available. So that gives this third inequality. 3X1 plus 2X2 is less than or equal to 18. Okay. These are the constraints on the numbers X1 and X2, which are the batch numbers. Now, this simple problem, I mean, it is simple because there are only two variables, X1 and X2. You can solve this graphically. You can draw in the plane the area in the plane, all the values x1 and x2, which satisfy the constraint inequalities. So the first step is to identify the values of x1 and x2 permitted by the restrictions. Okay, what are the restrictions? Well, here were 3 of the 5 restrictions. We don't use x and y, we use x1 and x2. So x1 is the horizontal axis and x2 is the vertical axis. So x1 is greater than or equal to 0. x2 is greater than or equal to 0. That means we're only looking at points in the first quadrant. And we also have x1 is less than or equal to 4. So we're in this infinite strip between the vertical lines x1 equals 0 and x1 equals 4, and above x2 equals 0. So this shaded area is the region in the two-dimensional plane, what you used to call the xy plane, and we'll call the x1, x2 plane. It's the region in this plane satisfies these 3 inequalities, these 3 constraints. But they're not the only constraints. We also have the constraint that says 2x2 equals 12, which is the same, or sorry, it's really 2x2 less than or equal to 12. So x2 less than or equal to 6. So if you draw the horizontal line, x2 equals 6, we're looking at everything in this rectangle. But we have the 3rd constraint, or the 5th constraint, if you like, the 3x1 plus 2x2 equals 18. This is the equation of a line in the plane. This is the line. And 3x1 plus 2x2 less than or equal to 18 means we're looking at everything below this line. So what is called the feasible region is all the points in the plane that satisfy our 5 constraint inequalities. x1 is greater than or equal to 0 and less than or equal to 4. x2 is greater than or equal to 0 and less than or equal to 6. And x1 and x2 together satisfy this inequality. So the most 3x1 plus 2x2 can be is 18. This is a straight line. If you graph it, you have to know the slope-intercept formula for the line. This is a line with slope equal to -3/2 and y-intercept 9. So the points in the plane that satisfy our 5 constraints is this gray region. It's a trapezoid. It's this gray region. And feasible means that any point in this region satisfies all 5 of our inequalities, and no point outside this region satisfies our 5 inequalities. So we have all the points x1 and x2 in this region, and each of those is a choice we could make for how many batches of product 1 and how many batches of product 2 we want our company to produce. And associated with every such point, for every choice of x1 and x2, is the profit that the company would generate from that allocation of resources. The value of Z that you get, the profit from producing x1 batches of product 1 and x2 batches of product 2. What is our objective function? It's Z equal to 3x1 plus 5x2. For example, if Z were 10, the equation 10 equals 3x1 plus 5x2, that's the equation of a straight line. This is a picture of the intersection of that straight line with the feasible region. For any point x1 and x2 that lies on this line, if you produce x1 batches of product 1 and x2 batches of product 2, your profit will be 10. That means $10,000. If we look at a different value of z, 20, for example, we get this line. Notice it's parallel to the first line, but z is bigger. So for any point on this line, the value of z is equal to 20. And we want to find the choice of x1 and x2, which maximizes the profit, gives us the largest value of z. And if you look at all these lines that are parallel, the higher up the line is, the greater the value of z. And the point in this feasible region, which hits the y-axis as the greatest possible point, is right here at this corner point, 2, 6. When x1 is 2 and x2 is 6, you get z equals 36. This says if you produce 2 batches of product 1 and 6 batches of product 2, you have a profit of $36,000, and that maximizes the profit over all possible choices of x1 and x2. So the solution of this linear programming problem is that x1 equal 2 and x2 equal 6. That gives you the greatest possible profit. So what were the steps involved in this problem? We had a business situation. Company has the ability to produce 2 new products. Its resources that can be allocated are time in 3 different factories. And for each product and in each factory, there's a certain number of hours of work that are required. There are constraints on how many hours of work each factory can allocate to producing these 2 new products. All the possible choices of x1 and x2 that satisfy the constraints lie in this gray area, which is called the feasible region. We have an objective function, which is the profit. And to every point in the feasible region, there's a profit. And we want to pick the point that maximizes the profit. And it turns out it's right here at this corner, 2, 6. So this is the graphical solution. That means we're drawing a graph. That's the graphical solution of this integer programming problem. Right? This is the prototypical example. And the first homework will ask you to solve a few problems of this type. And it just takes pencil and paper, or maybe pencil, paper, and a ruler, and a little bit of time. Having some graph paper is very useful. Makes it easier to draw good pictures. All right, this is the feasible region. And this is the feasible region with various choices of the objective function. So what is the language that we use in linear programming? So this is the general problem terminology and examples. The kinds of resources you might have: money, different kinds of machines, vehicles, personnel, activity, investing in particular projects, advertising, shipping. All these are possible activities. And the problem involves choosing the level of the activities that maximize the overall performance. So in our first example, our resources were the production capability of various plants. And we had 3 plants. That is, we had 3 different resources. Each plant was a resource. What were the activities? Well, the production of the different products. And how many activities were there? Well, there are 2 activities, 2 products, 1 for each product. And the production rate of each product, that was the level of activity. And the profit Z is, in this problem, was our overall measure of performance. So a typical linear programming problem will have the following standard form. You want to maximize some function Z which is a linear function of n variables, and you will have constraints. Constraints are some linear function less than or equal to b1, less than or equal to b2, less than or equal to b sub m. You might have little m constraints and certain non-negativity conditions. The x's have to be non-negative. Sometimes you want to minimize the objective function. So if the objective function measured cost, you might want to minimize your cost. You might have constraints which are not less than or equal to, but greater than or equal to. Or you might have some constraints which are equations, not inequalities. And occasionally the value of a variable might be negative. That's not typical, but it's certainly possible. A feasible solution is a solution where all the constraints are satisfied. If you're lucky, you have feasible solutions, but it might happen in a particular problem. There's no possible solution at all. There's no feasible solution. And an infeasible solution is a bad solution. It's a solution where at least one constraint is violated. Now you're always looking for the optimal solution, which is the most favorable value of the objective function. If it's profit, the most favorable value would be the biggest value. If it's cost, the most favorable value would be the smallest value, right? And you might have a poorly posed problem or be unlucky. And in some particular case, there might not be a solution. There's no optimal way to do it. That can happen. In many cases, especially if you're lucky, you will be able to look at just the corner points of your region. And a corner point feasible solution is a solution that's at one of the corners of the feasible region. That's what we saw in the window company problem we looked at a few moments ago. And this is really a key fact. In a linear programming problem that has a feasible region, that means it has feasible solutions, and the feasible region is bounded, the optimal solution, there can be more than one, but at least one will be a CPF, a corner point feasible solution. And the best corner point feasible solution will always be optimal. There may be a lot of them, but at least one of them will be a corner point solution. So this is sort of the background, and what we've just done is cover in chapter 3, sections 1 and 2. The most important thing is to understand how we set up the linear programming problem for the wind door glass company and solved it. And the homework, the first homework assignment, which will be due next week, will be some of the problems at the end of chapter at the end of chapter 3, and this will be posted on Blackboard. That's it.